Hello everyone, welcome back to my YouTube channel. In today's video we're going to be talking about a concept from complex analysis. In particular, we're going to be solving a question that uses the identity theorem. If you're a current student of mine in complex analysis, this question showed up on last week's homework. Otherwise, this is a very common type of problem and shows up on a lot of different types of exams. So in any case, I think this would be useful even if you're not currently in one of my discussions. So what's the question? The question is asking, does there exist an analytic function f in the disk modulus of z less than 1, let's call that set omega, such that f of 1 over 2k is equal to 1 over 2k, and f of 1 over 2k plus 1 is equal to 1 over 2k. And this is for k living in the set 1, 2, 3, and so on. So before we actually go through the solution, start thinking about whether or not such a function can exist and kind of what intuition do you have for this. And while you're thinking about that, let's review the identity theorem. So this is going to be the main tool we have to solve this type of problem. So suppose f and g are analytic functions on a domain omega. If f is equal to g on some s, which is a subset of omega, where s has an accumulation point, then f is equal to g on omega. All right, so let's actually go through the solution. So the way we're going to want to start this problem is let's suppose such a function exists. So suppose such f exists. And we want to use the identity function. So we need to find a function g that agrees with f on some s that has a limit point and is contained within omega. So a hint for this problem on kind of what s we want to use is let's take a look at 1 over 2k. So I claim that if I take the set of 1 over 2k for k living in 1, 2, 3, this has a limit point, namely 0. So if we draw a picture just to see what this looks like. So here's, let's say, 0. And we're starting at k equal to 1, and we're taking 1 over 2k. So we're going to have half. Then we're going to have 1/4. And we're going to keep getting smaller and smaller and smaller and approach 0. So notice that no matter how small of a neighborhood I take around 0, I'm always going to capture a point of the form 1 over 2k. So that's just an intuitive or cute little picture that shows this limit point or accumulation point. So that's kind of a hint for how we should be thinking about this problem. So remember, we need this s living in omega with a limit point. This is the one that we're going to want to use. So now we need to figure out what g do we want to use. So I'm going to say let g of z be equal to z. So g of z is entire. So that means analytic on all of c. So in particular, g of z is analytic on omega. And we also need that f and g agree on this set which contains a limit point. So this is where we're going to want to use this f at 1 over 2k is equal to 1 over 2k. So I'm going to say, notice f of z is equal to g of z on the set s equal to points of the form 1 over 2k for k equal to 1, 2, and so on. Why is that? Well, we know that f, let me do this in a different color. We know f of 1 over 2k is equal to 1 over 2k. And then g of 1 over 2k has to be equal to that as well, just by construction. We said g of z by definition is z. So then from our above observations, we know that s has a limit point. It's a subset of the unit disk. And we know that f of z and g of z are equal to each other on that set. So then the identity theorem implies f of z has to be equal to g of z on the whole set omega. So far we haven't done anything too crazy. We've found a g of z that agrees with f of z on a set that has a limit point, and we use the identity theorem to say, well, they have to be equal to each other on the entire space. But now let's say, on the other hand, so remember, we're assuming such a function exists. We know that f at 1 over 2k plus 1 is equal to 1 over 2k. But again, by our choice of g, we know that g of 1 over 2k plus 1 is equal to 1 over 2k plus 1. So what this means is that f and g disagree at the points 1 over 2k plus 1. And remember, just because 1 over 2k, and this should be 2k plus 1, cannot be equal to 1 over 2k plus 1 for k in the set 1, 2, ... But this is a contradiction. Because we said that f of z has to be equal to g of z on the whole space omega. So what goes wrong with the argument? It's our assumption that such an f of z exists. So we conclude no such f of z can exist. All right, everyone, I hope this video was useful. Like I said, there's a lot of variations on this type of problem. It's actually a very popular problem for complex analysis qualifying exams. Your choice of g of z won't always be as simple as just g of z equal to z. But this is kind of like a first good introduction to these types of problems. So I'll end the video here, and I will see you in the next one.